Okay, so let's do our second example for an independent measures t-test. That means we're going to have different subjects in each group, and this time we're going to do a t-test that has an unequal sample size for each of the groups. So this is work that was done by a psychologist by the name of Paivio, and the goal here is to try to determine whether or not people remember different types of words differently. Okay, so the experiment that we're going to do is we're going to manipulate the type of word that we present to the subjects. So some of the subjects are going to have what are called concrete words, and some of them will have abstract words, okay? And by concrete words, I mean words that you can sort of visualize. They're nouns, they're things that you can, create an image in your mind's eye. And then abstract would be words where it would be difficult to do that because they don't represent a tangible essence in a way, okay? So, for example, concrete would be words like house or dog or shoe, okay? And abstract might be words like hope or try or short, okay? What we're going to do is we're going to give each of the subjects a list of 20 words, either concrete or abstract. We're going to have them look at the words for, let's say, 5 minutes, okay, a list of 20 words. And then we're going to wait for, let's say, 10 minutes. We're going to ask them to recall as many words as they can from that list of 20. Okay, so that's the experiment. And so the data will show us how many words out of that list of 20, how many of the words they remember. So let's suppose that for the concrete words, we see these kinds of recall numbers: 7, 8, 7, 6, 9, 8, and 7. All right? And if you recall from maybe taking intro to psychology or something like that, there is something about this sort of 7 items plus or minus 2 that psychologists talk about. It's not really as clean as it is sometimes presented, but so you'll see people might remember about 7 words out of that list of 20 when they're concrete words. When they're abstract words, let's say that we see these numbers of words recalled: 6, 7, 4, 6, 6, and 5. Okay? Now, 1, 2, 3, 4, 5, 6, 7 people in this group. 1, 2, 3, 4, 5, 6 people in this group. Okay? So we have n equals 7 here, n equals 6 here. This is the number of people in the group. Okay? And what we're going to do is we're going to see if there is a difference between the averages for the two groups. Or another way to think about that is we're going to look at the average difference between the two groups. Okay? And let's do our 5-step hypothesis testing procedure. Let's set up our null hypothesis, which would state that the concrete word population and the abstract word population are going to have equal means. Another way of writing that is that the difference between the two groups is going to be 0. When we compare the two groups, we're going to find no difference, 0. Okay? So the alternative hypothesis then would be that the people who are exposed to the concrete words will have a different level of recall than those presented with the abstract words. Okay. Again, I'm going to do this as a non-directional hypothesis, or sometimes called a bidirectional hypothesis. And if we have time, I think we will, I can show you how to do a directional hypothesis, even though sometimes that's not the best way to do the analyses. Okay, I think the general, sort of the typical way is to do a non-directional or bidirectional. Okay, those two are the same things. When I say non-directional, I mean I'm not choosing a direction that I think the data are going to, show a difference in one direction. When I say bidirectional, what I'm doing is I'm testing for significance in each direction. Okay, plus or minus the critical value. Another way that I can write this is to say that if I compare the concrete population mean to the abstract population mean, I'm going to get something other than 0. That is, I'm going to find some difference, right? Instead of no difference, I'm going to find some non-zero difference there. Okay? So those are the two hypotheses. Same thing we've done for a while. Now let's do our step 2, and that is we're going to decide on an alpha level, and for our purposes, we're going to use the standard alpha level of 0.05, and that means that I'm going to reject the null hypothesis as long as the t-value goes into the extreme 5%. All right? And so we need to get our critical t-value. We're going to use a t-test here because we don't have the population parameters. That is, we don't have mu, we don't have sigma. Okay? And in fact, we know what degrees of freedom we would use here, and that would be the degrees of freedom for the concrete group, which is n-1, and in this case 7-1, which is 6. So degrees of freedom here are 6. For the abstract group, it's n-1, so my degrees of freedom here, 6-1, or 5. When we get our critical t-value, we get our observed t-value. We're going to combine these degrees of freedom. So we have 11 degrees of freedom for this experiment, okay? And we can look up the critical value. This is going to be in the table in the back of your book, or I'm going to use my little handy-dandy excerpt from that table. Look at the degrees of freedom on the far left-hand column. We'll go down until we see 11 for our degrees of freedom, and then our critical value plus or minus 2.201. Okay, and if you recall, we should remember that it's going to be 2 point something for any reasonable amount of number of degrees of freedom. We have 2 point something something. We'll go all the way down degrees of freedom of infinity of 1.96. That would mean that we're using a z-score. Okay, so now we can start this way. Our t-value is going to be the mean for the first group minus the mean for the second group. We're going to divide that by S sub M1 minus M2. Okay, we'll get to that in a minute. Let's first do our means for the first two groups, or for these two groups here. So the mean for the concrete, the mean for the abstract group. And once again, I mean, there's no particular reason why I have the concrete group first and the abstract group second. I could put the abstract group first and the concrete group second. It just doesn't really matter. But let's get the mean here. 15 plus 13 plus 17 plus 7 equals 52 divided by 7. So the mean here is 7.43. And I'm just going to quickly check that. 7 plus 8 plus 7 plus 6 plus 9 plus 8 plus 7 equals 52 divided by 7, 7.43. Okay? The mean for the abstract group, 13 plus 10 plus 11, 34, divided by 6 now, remember. So the mean here is 5.67. Okay, 5.67. I'm going to double check that. 6 plus 7 plus 4 plus 6 plus 6 plus 5 equals, divided by 6 equals 5.67. So I have my numerator here, 7.43 minus 5.67, okay? So that's, I think, pretty straightforward, easy to get the means. I'm hoping that conceptually it is somewhat intuitive. I want to know if there's a difference between the average number of words recalled here and the average number of words recalled here, right? And so this is looking at what that difference is. Now what I need to do is figure out, well, okay, here's a difference. It's not 0, but we need to compare that to the variability of the groups. The variability of the groups we need to compare that to. And we're going to get this variability by doing two things. First of all, making a guess about what sigma is. And in this case, we're going to make a guess about what sigma squared is. And we're going to give that a symbol of s squared. Okay? But first things first, let's do this. Our basic building blocks for variability. See, we could go all the way back to chapter 4 and talk about sum of squares, right? And the basic building block is x minus mu, and we're squaring it because we want to get rid of the negatives, right? And then we're adding them all together and so on and so forth. Let's just do this as a reminder of the sum of squares formula. Okay, I can get this easy, by the way, because it's 7.43 times 7, okay, 52. So this is 52 squared. I'm getting 52 by multiplying this by 7. It gives me 52. Okay, 52 squared, okay, divided by 7 equals. So this is 386.29. All right. And by the way, if you want to stop the video and do these computations on your own to see if they match with what I'm coming up with, I would highly recommend that. Remember that this part is squaring each of the numbers and then adding it together. So let's do that. Boy, I'm glad I know my squares. Hint, hint, okay? 49 plus 64 plus 49 plus 36 plus 81 plus 64 plus 49 equals 392 minus 386.29. And that gives us a sum of square of 5.71. Okay? Pretty small compared to what we've seen in some of our other examples, but these numbers are quite close together. Okay? And so that should make a little bit of sense to us. For the second group, let's see if we can do it. Again, if you would like to pause the video, see if you come up with the same number that I come up with. Let's start by getting the overall sum of the x's. I do 5.67 times 6. So that's 34. That's this number. 34 squared divided by 6 now. Keep your wits about you, okay? So this is 192.67. Then I'm going to do this. 36 plus 49 plus 16 plus 36 plus 36 plus 25 equals 198. Okay? I'm just going to double check that. Why wouldn't I? 36 plus 49 plus 16 plus 36 plus 36 plus 25, 198 minus 192.67 equals 5.33. Okay? So those are our sum of squares. And what we're going to do then with those is we're going to pool the variability. Okay? We've talked about this before in the last video. We're going to pool the variability together. And this is based upon an assumption, okay? Really some logic here. If we fail to reject the null, what we're going to say is these two samples came from the same population, right? If we fail to reject, we're saying there's no difference between these two, it's the same population. If that's the case, if we fail to reject the null, then these two variabilities should both be guesses about, or we can use the building block as guesses for the same sigma. Okay? The question is, well, what if they came from different populations? Well, everybody remember? Even if they came from different populations, what we're going to assume is that the treatment, in this case, rather than concrete, if we give abstract, the treatment will cause the recall distribution to shift downward or upward, but it won't cause changes in the variability. If that's the case, then both of these variabilities should give us a guess at the same sigma. Okay? So, that is, we're assuming that the treatment just pushes the curve up or down the number line, it doesn't change the variability, okay? And because we have that assumption, we also will then assume something called the assumption of homogeneity of variance. And that is, we assume that there will be approximately equal, I like to say equivalent rather than equal, we should have approximately equal or equivalent variabilities of these two groups, even if the means are different, right? That's based on the logic that the treatment is just going to shift the curve, it's not going to change variability, if there is a treatment. If there is no treatment, then we should have samples from the same population. So we assume homogeneity, same, okay? Homogeneity of variance. Doesn't have to be equal, but it should be equivalent. If that assumption is violated, I mean, if we had a sum of squares here of 265 and a sum of squares here of 13, then this assumption might not be valid. What we do in a t-test relies on the assumption of homogeneity of variance. Okay? If there's reason to believe that this assumption has been violated, then we would need to do a different statistical test. Okay? So let me go through this again. We're going to combine these variabilities because we have an assumption of homogeneity of variance. They should reflect the same variability. But why do we make that assumption? That's the assumption, but why do we make that assumption? Well, there's two possible outcomes, right? If we fail to reject the null, these two came from the same population, so they should have about the same variability. If we reject the null, that we're saying these two came from two different populations. If we reject the null, though, we're assuming that the treatment just pushes the curve up or down, and so we should still be able to make this assumption of homogeneity of variance. But if the data show us something different, if we suspect that we might not have this, then we would need to do a different statistical test. Okay? Now, there is a test you'll read about, something called Hartley's F-max test. Hartley's F-max test will test for this assumption of homogeneity of variance. It will say, listen, if I had a sum of squares of 212 here and a sum of squares of 13, then I don't think I have homogeneity of variance. I can apply this test. We're not going to do this, but I want you to know what this is for. Everybody get it? Wink, wink. We're not going to do the test, but Hartley's F-max is a test that you use to see if there's homogeneity of variance. If you find that you don't have homogeneity of variance, then we can't do a t-test. For our purposes here, we're going to assume homogeneity of variance. They look pretty similar, but remember, this is only from 6 people and this is from 7. So there's a little bit more variability here than here. But you'll have to trust me on this one. I'd rather not open this tool right now. We'll leave it shrink wrapped. We'll just assume that we have homogeneity of variance, but it's very important. We'll assume that we have that. We won't need to do this for right now. And by the way, mathematicians usually refer to this, when we're doing this research stuff, this assumption is typically what's called a robust assumption. In other words, you have to have really dramatically different variabilities to violate this assumption. Okay, so we need to get this value, but in order to get that value, right, if we look at the formula, here's what the formula looks like, okay? In order to get this value, we need to get the sum of products, the pooled variability. We need to get the pool variability first. And so what is the pooled variability? Well, it's the sum of squares for the first group plus the sum of squares for the second group divided by degrees of freedom for the first group plus degrees of freedom for the second group. Everybody with me? Pooled variability, pooled variance. So 5.71 plus 5.33 divided by 6 plus 5. The degrees of freedom for the first group, the degrees of freedom for the second group. You do not have to memorize these formula, but you have to be able to use them. Okay? We're adding these together, then dividing them by the addition of these together. So it's 5.71 plus 5.33 divided by 11. Let's do that. 5.71 plus 5.33 equals 11.04 divided by 11 equals 1. Well, that's kind of weird. I didn't do this before I put the numbers up. This equals 1. 1. Okay? Now we put this value into here. So this is, remember, this is just a subscript. So we're going to do 1 divided by 7. Remember now, this is n, not degrees of freedom, plus 1 divided by 6, and then we'll take the square root of that, okay? So 1 divided by 7 equals 0.14. 0.14 plus 1 divided by 6 equals 0.17. We'll add those together. 0.14 plus 0.17 equals 0.31. But remember, we got to take the square root of that. And so our value is 0.56. Let me get my eraser. 0.56 is my value for this. Put it here. Just take your time, and you're going to need to be organized when you do this. You're going to need to be organized, okay? So first we got the sum of, the pooled variance, and that was equivalent to our guess for S, but it's actually our guess for S squared in this case. Our guess for S was our first step. Well, our first step was our building blocks. But here's our guess for our S, and then this becomes our central limit theorem treatment, right? We got our guess for S, now we need S sub M, okay? And that's, so 2 steps, boom, boom, from our building blocks. Now we can get our observed value of T, 7.43 minus 5.67 equals, divided by 0.56. So there's our T value, and in this case it's positive. All that tells us is that this group, the first group, is bigger than the second group. So people are remembering more of the concrete words than they're remembering of the abstract words, okay? I'm going to compare this value, of course. I'm going to compare this value, hold on a minute, to my critical value, okay? Here's the critical value. Here's my observed value. Let's get rid of this. Let's just remind ourselves what this means, right? Here's our critical values. And our value is out here somewhere, okay? So that's telling us this is a difference that we wouldn't expect. These are expected differences. Here's where we're at. So there's something going on here. If I'm treating these two groups of people in the same way, except one group gets concrete, one group gets abstract, then I can say, well, people remember concrete more. Now, when I do this research, by the way, I'm absolutely going to make sure that for example, the number of syllables for each of the word lists is the same. Because I don't want this to represent, well, fewer syllables here or more syllables here, right? Or something like that. So, but that's a research methods concern. But we have to make sure that we pay attention to that, okay? Because if you have a bad experiment, then it doesn't matter what statistics you do. It doesn't matter what statistics you do. If you have a bad experiment, you're shot, okay? You're done. All right? So, in this case, our observed T is larger than our critical T. And so what are we going to do in terms of the null hypothesis? Yeah, we're going to reject the null. And if you look back at your notes, the null said that the concrete population and the abstract population, in terms of recalled number of words, they would be equal. We're rejecting that. They're not equal, okay? They're statistically significant. So let's do this. Let's do this. And now, of course, I'm going to make my conclusion. All right, I'm going to make my conclusion. And it appears that, and sometimes people will ask me, do you always start with that? Well, I mean, it's appropriate to say it appears because this is ultimately a probability statement, but it's a pretty strong, pretty informed statement, okay? I tend to use these as my first three words. I'm just in the habit of doing that. I think it sets us up for an acknowledgement that it's really probabilistic, okay? It appears that concrete words are recalled better, I guess. Is that what we want to say? Are recalled better. Or subjects recall concrete words more, or something like that. There's no, sort of correct verbiage. I think this works. And I'm always willing to revise, too. It appears that concrete words are recalled better than abstract words are recalled, let's say, significantly better. That's a word, that's kind of a statistical word, right? It appears that concrete words are recalled significantly better than abstract words. And this is why I'm saying this. I did a t-test with 11 degrees of freedom, and my result was 3.14. And what that tells me is that goes into the extreme 5% of my distribution. Okay, the probability that the null hypothesis is true is less than 5%, is what I'm saying. Also notice, like I've mentioned before, I'm putting here in my parentheses, I'm putting in the observed value. This is the reference value. This is what I observe from my data, okay? This is such a large value that it would actually surpass the 0.01 level. And you can look at that in your appendix, in the book, in the t-test table. If you look at 1% in both tails, okay, you'll find that we're going to be beyond that with 3.15. And so I might do something like this. If I was doing this research, instead of 0.05, I would put p less than 0.01. I'm not going to do that for this class, but you'll see it in the literature. That's why I do it. And I'm hoping that if you understand the concept, you'll understand why this is so far out that I could put p less than 0.05. It's going into the extreme 1% of the distribution. Okay? This is how you do a t-test for two groups. They have different subjects. This time I used different size samples, which is absolutely okay. There was a professor in my department, a professor teaching this course, and she was telling students that you couldn't do a t-test with different size samples. And this is not my opinion. She was incorrect. She was teaching students incorrectly. And she said, if you have 7 in this group and 6 in this group, you should get rid of one of these. And I'm like, wow, what? Get rid of one of these? If you get rid of data, if you lower your sample size, what happens to power? Power will go down. Why would you do that? Oh, makes me crazy. But if you recall this formula, right? The pooled variability over N1, the pooled variability over N2. Guess what? Right here. I mean, if you always had to have the same N, then the formula would just be 2 times sum of products over N, right? But that's not the case. You can absolutely have different sample sizes, okay? In general, when you're doing research, you sort of want to have kind of an, similar number in each of the groups. That's absolutely what you would like to do. If I have 7 in this group and 6 in this group, I can absolutely deal with that. Okay? 2 groups, use a t-test. 2 groups, if you want to find the difference between 2 groups, use a t-test. T-test. Okay? In fact, some of you may know this song. Let's see if I can do it. Now some of you are like, wow, Dr. Speck has lost his damn mind. Okay? Anybody know the title of that song? It's called T for 2. Because a lot of times people come out of this class, even if you get an A, and you're like, I learned the stuff and I got an A, but I don't know when to use what. If you're trying to assess whether there's a difference between 2 groups, you use a t-test. T for 2. Da, 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 da. Hopefully that will serve as a memory jog for you. It's like that song, T for 2, T for 2 groups. And this is how you do it. Whether you do in psychology, biology, physical therapy, chemistry, business, criminal justice, nursing. If you have 2 groups and you want to know whether there's a difference between the 2 groups, use a t-test. Okay? So we'll talk on the next video about another sort of style of t-test, and I'll show you what that's all about. Still with 2 groups, T for 2.